This is the second part of lecture 17 related to the principle of general covariance. And so we're going to talk about GR tensor equations that's obey the principle of general covariance. And not only we'll talk about GR equation motion, but later on we can talk about GR field equation. And useful here is the idea of so-called minimal substitution rule. According to the strong principle equivalence, gravity can always be transformed away locally. Okay. As first this in chapter 5, Einstein suggests an elegant formulation of new theory of gravity based on curved space and time. Okay. In such a theory, the equivalent principle is fundamentally built into the theory because the flattened theorem in the metric structure of space-time means that special relativity, the theory of flat space-time with no gravity, is automatically incorporated into the new theory. And gravity is modeled not as a force, but as the structure of space-time. Free particles just follow the geodesic in a curved space-time. Okay. The principle of general covariance and in the field equation for the metric function, so it was the gravitational field is the metric function, which is solution to the field equation. Okay, must have the field equation must have the same form no matter what generalized coordinates are used to label the world points, events in space-time. One expresses by requiring that the physics equation must satisfy the principle of general covariance. So first, geometric statement, and then translate into physics. This principle has two parts. One is the physics equation must be covariant under general coordinate transformation, which leaves infinitesimal space-time line of ds squared invariant. Second part, the physics equation should reduce to correct special relativity form in the local inertial frame. Namely, it must have the correct special relativity equation in a free fall frame. Additionally, gravitational equation must reduce to Newtonian equation in the limit of low velocity particles in the weak and the static field. The Newtonian limit we talked about. Now we talk about so-called the minimal substitution rule. This general principle and provides with a well-defined path to go from special relativity to general relativity. Special relativity value in the local inertial frame with no gravity, and the general relativity as the case value in every coordinate frame in the curved space-time. It's curved because we have gravity now. And GI equation must be covariant under general local transformations. The key feature of general coordinate transformation, in contrast to, for example, Lorentz transformation in the flat space-time, is it's space-time dependent. Because curved space, the basis of position dependent, so therefore the transformation is not necessarily position dependent. And this implies that we must use covariant derivatives in order to keep tensor structure. So to go from special relativity to general relativity, we need just make substitution of ordinary derivative by the covariant derivative, which is ordinary derivative plus the Christoffel symbol. This is known as the minimal substitution rule because we assuming there's absence of higher order, for example, Riemann tensor terms, because those terms are vanished in the special relativity. You can never see it. There's nothing you can. So it's absent from special relativity. So there's no substitution you can lead to. So, but we assume they are not there. So that's why it's called the minimum substitution rule. Now, Christoffel symbol are the first derivative of the metric. So therefore, metric is potential. So therefore, they represent gravitational field strength. So the introduction of covariant derivative naturally brings gravitational field into the physics equations. For example, the minimal rule leads to say, if I know the Maxwell equation, the Gauss-Ampere's law, works in the absence of gravity. Now, if I want to know what is the Maxwell's equation In the presence of gravitational field, all you have to do is replace the ordinary derivatives by covariant derivatives. Okay, and of course the covariant derivative has two parts: ordinary derivative plus the Christoffel symbols for each of the indices. So this is the equation for. Of course, all these works only if you know the special relativity equation. Okay. And also another comment I want to make. Remember, we says the double commutative covariant derivative acting on the vectors leads to Riemann tensor is related to the parallel transport of vector around a closed path, and this substitution rule will help you to understand why they're related. So after substituting ordinary derivative by the covariant derivative, the displacement of a vector by dx may be written schematically like this. If I a value x plus dx, then it's equal to a of x plus first derivative, but now the derivative is replaced by covariant derivative. Okay, dx covariant derivative act on a. Or I can write this as factor out the field a is 1 plus dx, the covariant derivative dx. So now we will talk about closed path. The transport vector around closed path can be spanned by dx dy can be expressed this. Okay. First transport, well, actually it should be dx, then followed by dy, and so these are the displacement factor, and going the other way is just interchange x and y, and it's minus sign, so 1 plus dy and 1 plus dx. And when you take them out, of course, the one term cancel, and also the linear term cancel. So dx, capital dx, this term here, is cancel the minus dx, capital dx. So only to survive the quadratic term, which have dx dy, so this becomes a commutative covariant derivative acting on a. So therefore, the parallel transport vector through a closed path is closely related to the idea of a commutator of covariant derivatives. Now we can talk GI equation motion. Now, gravity in Einstein theory is not a force, but the structure of space-time. So therefore, the motion of particle, if only there's gravity, is the motion of free particle, because gravity is not a force in the space and time. At this point, instead of arguing heuristic as we did in chapter 5 that the geodesic should be the equation of motion, the minimum substitution rule actually provides us with a formal way to derive this conclusion. Okay. The argument goes like this. There are special relativity equation motion for a free particle is saying the derivative of the full vector equals 0. For acceleration, tau is the proper time, and x dot is the full velocity of the particle. So that's the equation for a free particle. To go from special relative to relative, we're simply replacing the ordinary derivative by covariant derivative. Okay. So this is the equation of motion, the free particle in GR. And you write it out, the covariant derivative is first ordinary derivative plus the Christoffel symbol term. So you notice that's just the geodesic equation. So therefore, this naturally is the equation of motion for GR. Okay, this middle part of chapter lecture 17.